Welcome to today's lecture. Welcome back to our lecture exam. This next problem is going to ask you to use the method of undetermined coefficients to solve an initial value problem. Second order ODE equals a function negative 35 e to the 2x, and y of 0 is equal to 1, y prime of 0 is equal to negative 7. The associated homogeneous equation is y double prime plus 8y prime plus 25y is 0. It has p of r is r squared plus 8r plus 25 is the characteristic polynomial. Its roots are obtained from the quadratic equation. R is negative 4 plus or minus 3i. Negative 4 coincides with the solution e to the minus 4x times sine of this coefficient of I, sine of 3x, and cosine of 3x. So we saw before, when we have roots of the characteristic polynomial that are complex conjugants, negative 4 plus or minus 3i, we get solutions that look like e to negative, the real part, negative 4x, plus times cosine of the imaginary part, 3 in this case, times x, cosine of 3x and sine of 3x. So this 3 goes in the input for sine and also the input for cosine. The next step is to find a particular solution using the method of undetermined coefficients. So here, this solution, yc, is c1 e to the negative 4x cosine 3x plus c2 e to the minus 4x times sine 3x is a solution of the general solution to the associated homogeneous equation. Y double prime plus 8y prime plus 25y is equal to 0. Now, because when you differentiate this function on the right-hand side, negative 35 e to the 2x, you don't get any more linearly independent functions besides constant multiples of e to the 2x. So the method of undetermined coefficients says we should write, as long as e to the 2x doesn't appear as a function in the general solution to the associated homogeneous equation, we should write yp as constant multiples of all the function on the right-hand side and all of its linearly independent derivatives. But here, there's only one function that we get from differentiating, and that's e to the 2x. So method of undetermined coefficients says we get yp as a times e to the 2x. We therefore compute yp prime is 2a e to the 2x. Yp double prime is 4a e to the 2x. We plug these functions back into the original equation, the non-homogeneous ODE. We get yp double prime is 4a e to the 2x. Yp prime is 8 times 2a e to the 2x. And yp is 25a. So we're left with 4a plus 16a plus 25a times e to the 2x. We get 35a times e to the 2x. That's equal to negative 35 e to the 2x. When we set the coefficients of e to the 2x equal to each other, we get 35a equals negative 35. That means a is negative 1. So yp is negative e to the 2x, and we get the following general solution. c1 e to the minus 4x times cosine 3x plus c2 e to the minus 4x times sine of 3x minus the 2x. So this is the general solution of the non-homogeneous ODE. It consists of the solution, the general solution of the associated homogeneous equation, plus the particular solution, negative e to the 2x. We plug in the initial condition y of 0 is 1. We get c1 minus 1 is 1, or c1 is equal to 2. Therefore, we get y of x is 2 e to the minus 4x times cosine of 3x plus c2 e to the minus 4x times sine of 3x minus e to the 2x. So notice When we plug in x is equal to 0, the first term becomes c1 because e to the 0 is 1. Cosine of 0 is also 1. When we plug in 0 to the second term, we get e to the 0, which is 1, times sine of 0, which is 0. Therefore, the second term vanishes. We're subtracting e to the 0, which is 1. So we're left with c1 minus 1, which is equal to positive 1. Therefore, c1 is 2, and we get 2 e to the minus 4x times cosine 3x plus c2 e to the minus 4x times sine 3x minus e to 2x. Now, when we differentiate the function, we get all these terms. But when we plug in x equal to 0, the second term and the third term are going to vanish because they include factor of sine, and sine of 0 is 0. So we're just left with the first term, the fourth term, and the fifth term. The first term becomes minus 8 because e to the 0 is 1, and cosine of 0 is also 1. The fourth term becomes 3 times c2, again, for the same reason. E to the negative 4 times 0 is 1. Cosine of 3 times 0 is also 1. So this becomes minus 8 minus 2 plus 3 times c2. So we get negative 10 plus 3c2. Now we're given y prime of 0 is minus 7. When we plug that in, we get negative 10 plus 3c2 is negative 7, or 3c2 is 10 plus minus 7. That's just from adding this 10 to both sides. That means if 3c2 is equal to 3, it means c2 is equal to positive 1. That's from dividing both sides by 3. We therefore obtain the following solution. c1 is 2, and c1 is 1. So our solution is 2 e to the minus 4x cosine 3x plus e to the minus 4x sine 3x minus e to the 2x. So that was the technique of method of undetermined coefficients. You've noticed in exam 2, you had an extra credit problem that was about the method of variation of parameters. Here, and on your final exam, it's not going to appear as an extra credit problem, but rather as a 4-credit problem. Our job here is to find a 2-parameter family of solutions to the following equation. Y double prime minus 3y prime plus 2y is 1 over 3 plus e to the minus x. The associated homogeneous equation is y double prime minus 3y prime plus 2y is equal to 0. It has the following characteristic polynomial. R squared minus 3r plus 2 equals r minus 1 times r minus 2. Okay, that characteristic polynomial is factorable, so we just read off the roots 1 and 2. And we can just say, okay, place these roots in the exponent for e, exponent of e, and make them coefficients of x. So they're going to become the linearly independent solutions to the non-homogeneous equation are e to the x and e to the 2x. Therefore, the general solution of the associated homogeneous equation is c1 e to the x plus c2 e to the 2x. When we use the method of variation of parameters, we set the particular solution to be u1 times y1 plus u2 times y2, which is u1 times e to the x plus u2 times e to the 2x. And we solve the following system. u1 prime y1 plus u2 prime y2 equals u1 prime e to the x plus u2 prime e to the 2x is equal to 0. And u1 prime y1 prime plus u2 prime y2 prime equals the function that's on the right-hand side that makes this equation the second-order linear ODE non-homogeneous. So this function on the right-hand side, the book calls it q of x. We set u1 prime, y1 prime, plus u2 prime, y2 prime equal that function. And the first equation is always going to be 0. u1 prime, y1 plus u2 prime, y2. Notice here, u1 prime e to the x plus u2 prime e to the 2x. That's just plugging in y1 is e to the x, y2 is e to the 2x. y1 prime is e to the x, y2 prime is 2 e to the 2x. Now, if we subtract equation 1 from equation 2, these terms that are circled here become 0. And we're left with 2 u2 prime e to the 2x minus u2 prime e to the 2x. 2 minus 1 is 1, so we're left with u2 prime e to the 2x is just this function, 1 over 3 plus e to the minus x. So, multiplying both sides of this equation here by e to the minus 2x, we get u2 prime is e to the minus 2x over 3 plus e to the minus x. Therefore, u2 prime is negative 3 e to the minus x over 3 plus e to the minus x plus e to the minus x. Now this is because when we put e to the minus x in a fraction with 3 plus e to the minus x in the denominator, we get 3 e to the minus x times 3 plus e to the minus x over 3 plus e to the minus x. When you multiply e to the minus x by 3, you get 3 e to the minus x, so that cancels with this negative 3 e to the minus x. When e to the minus x is multiplied by e to the minus x, the exponents are added. That's just laws of exponents. So we're left with e to the minus 2x. And that's, of course, what was originally in the numerator. So e to the minus x times e to the minus x comes e to the 2x. This other term vanishes, is canceled by e to the minus x times 3. When we integrate u2 prime, we just get u2 is 3 times ln of 3 plus e to the minus x. So the antiderivative of minus 3 e to the minus x over 3 plus e to the minus x is 3 ln 3 plus e to the minus x. The antiderivative of e to the minus x is negative e to the minus x. Now, so we solve for u2. u2 prime e to the 2x is 1 over 3 plus e to the minus x. We put this into the original equation, and this gives u1 prime e to the x plus 1 over 3 plus e to the minus x is 0. That means u1 prime e to the x is equal to 1 negative 1 over 3 e to the minus x. So u1 prime is negative e to the minus x over 3 plus e to the minus x. Anti-differentiate or find the antiderivative, or just in antiderivative. Here, for method of variation of parameters, it's important we don't have to worry when anti-differentiating to add the integration constant c. So we're left with ln of 3 plus e to the negative x. We plug in u1 of x is ln of 3 plus e to the minus x, and u2 of x is 3 ln of 3 plus e to the minus x minus e to the x minus e to the minus x into our formula for yp, u1 y1 plus u2 y2. y1 is e to the x, so we multiply e to the x by ln of 3 plus e to the minus x. Okay, everything's good there. We can't really simplify that term any further. And we plug in 3 times ln of 3 plus e to the minus x minus e to the minus x for u2. That's multiplied by y1, which is e to the 2x. This becomes e to the 2x times this whole expression, and we distribute e to the 2x to each term. It's distributed to the first term, 3 times ln of 3 plus e to the minus x, and the second term, minus e to the minus x. Multiplied by the first term, we get 3 e to the 2x times ln of 3 plus e to the minus x. Multiplied by the second term, we get e to the x. Therefore, we get a two-parameter family of solutions to the following ODE. It's just yc, the solution of the associated homogeneous equation, plus the particular solution, which is e to the x times ln of 3 plus e to the minus x plus 3 e to the 2x times ln of 3 plus e to the minus x minus e to the x. And there you have it. That's how we found a two-parameter family of solutions to the ODE using the method of variation of parameters. And that's important because this function here, 1 over 3 plus e to the minus x, if we keep differentiating, we'll actually get infinitely many linearly independent derivatives. So that's what method of variation of parameters is used for. We can't use method of undetermined coefficients because that's going to give us infinitely many functions and infinitely many coefficients. So that's not going to be useful. Okay, number 6, and the last problem that is not an extra credit problem, is to solve the following initial value problem using Laplace transform. Y double prime plus y equals cosine of x. Y of 0 is 1, y prime of 0 is negative 1. Solution is to take the Laplace transform on both sides. L of y double prime plus L of y is L of cosine of x. S squared times L of y minus S y of 0 minus y prime of 0 equals S squared L of y minus S plus 1. And L of cosine of x is S over S squared plus 1. So we obtain S squared L of y minus S plus 1 plus L of y. That becomes S squared plus 1 times L of y because we are collecting the terms that have a factor of L of y. Minus S plus 1, so that came from negative S times y of 0. Y of 0 is positive 1, so minus S y of 0 just becomes minus S. And y prime equal to negative 1, that makes y prime of 0 equal, now minus y prime of 0 equal to positive 1. Subtracting negative 1 is the same as adding 1. So we're left with S squared plus 1 times L of y minus S plus 1 is equal to S over S squared plus 1. Now we're going to bring minus S plus 1 to the right-hand side here, and it's going to become S minus 1. And then we're going to divide both sides by S squared plus 1. So we get S over S squared plus 1 squared plus S over S squared plus 1 minus 1 over S squared plus 1. Now we just take the Laplace transform of each term. Now, if you look at the Laplace transform table, what do we find? So actually, if we go back to that table, we're looking for inverse Laplace transform of S over S squared plus 1. So notice here, okay, this is almost right with A is 1, but we have a 2 here. So if we divide by 2, if we divide this by 2, we're also going to divide the function on the right-hand side, by the left-hand side by 2. So it's important that even though we have this table of Laplace transforms, if we multiply any function on the left-hand side by a constant, that's going to multiply the function on the right-hand side by the same constant. And vice versa. If we multiply a function of s on the right-hand side by the constant, in this case a half, we're going to multiply the function on the left-hand side also by 1/2. So that means the inverse Laplace transform of 1/2 times 2s over s squared plus 1 in parentheses squared is 1/2 times x times sine of x, where a is equal to 1. So we find the inverse Laplace transform of s over s squared plus 1 squared is 1/2 x times sine of x. The inverse Laplace transform of s over s squared plus 1 is cosine x. You can just look at that in the table. Inverse Laplace transform of 1 over s squared plus 1 is sine of x. When we plug these functions back into the original equation for y, here's the equation for y, we just get 1/2 x times sine x plus x minus sine x. So notice it's true. You could have just solved this problem using method of undetermined coefficients, but it would have taken a while. You would have had to have, okay, ax cosine x plus bx cosine y, and then solve for a and b. This probably would have taken up more than one page. Laplace transform allows you to write down the solution in only one page. That's the power of the Laplace transform. And especially with initial conditions, we would have had to solve for a and b, and then solve for C1 and C2. That's going to take up at least 2 pages. So, or at least the page and a half. Okay, so that's how we can use the Laplace transform to solve a second order non-homogeneous ODE with 2 initial conditions. Okay, and those are the 6 techniques that are going to be tested on your final exam. First is separation of variables. Second is homogeneous equations, where you make a substitution and then the equation becomes separable. Third is integrating factors and the Bernoulli equation. Fourth is method of undetermined coefficients. Fifth, method of variation parameters. And sixth, Laplace transform. So notice all those topics, those 3 topics, method of undetermined coefficients, method of variation parameters, and Laplace transform, are all ones we've covered since the second midterm. Now, this 15 points extra credit. So this is based on last week's lecture. To use the power series to find a solution of the following ODE. xy double prime plus y prime minus 2y is 0. Subject to the following initial conditions. Y of 0 is 1, y prime of 0 is 2. You can write these terms using a power series. You can write the terms in the power series using a recursive formula for am plus 1 in terms of am. Note that y is equal to a power series. Y of 0 is a0, and y prime of 0 is a1. Why? Well, if y is this power series, and we plug in x equal to 0, all the terms are going to vanish because 0 to any power is 0 except, so 0, 0 squared, those are all 0, but the convention is that x to the 0 is equal to 1. So if x to the 0 is equal to 1, that means y of 0 is equal to a0, because the only term that's going to be left is a sub 0. Now y prime of 0 is a1. And that's because, if you look at this formula here, for y prime, we differentiate term by term. Remember, plugging in 0 for x and raising 0 to any power other than 0 is going to give 0. So the convention is that x raised to the 0th power is 0, so the only term we're going to be left with occurs when n is equal to 1. And it turns out when n is 1, n is 1, 1 times any number is that number, or variable, so we're left with 1 times a sub 1. And therefore, 1 times a sub 1 is the term we get when we plug in x equal to 0 to y prime of x. So with these formula for y prime, and y double prime, n times n minus 1 times an x then minus 2. So notice also, it also would be true, it's not written here, but also would be true if we wanted to do y double prime of 0, that would be equal to a2. And that's a2 because when we plug in x equal to 0 here, everything, when x is raised to a power that's larger than 0, we get 0. But if n is 2, we get 2 minus 1, which is 1, times 2. So, sorry, y, that wasn't quite accurate. Y double prime is not equal to just a2. It's actually equal to 2 times a2. Okay. Now we don't have to worry about that for this particular equation because we're just given, it's a second order ODE, we give an initial condition at 0, and for the function evaluated at 0, and for the derivative of the function also evaluated at 0. Now xy double prime is equal to x times the sum from n equal to 0 to infinity, n times n minus 1 times an to the times x then minus 2. N times n minus 1, an times x then minus 2. Notice laws of exponents, x times x then minus 2 is the same as x then minus 1. N times n minus 1 times an times x then minus 1. We sum from n equal to 0 to positive infinity. When we set m to be n minus 1, the above equation gives the following. X times y double prime is the sum from m equal to 0 to positive infinity of m times m plus 1 times a sub m plus 1 times x to the m. So that's because if m is n minus 1, then n is equal to m plus 1. So this n became m plus 1. n minus 1, of course, was just m. And we just rewrote it in slightly different order. m times m plus 1 times a sub m plus 1 times x to the m. We can rearrange the order because multiplication, of course, is commutative. Now, we do the same thing for y prime. Y prime, just this formula, infinite sum, index goes from 0 to infinity, n times an times x to the minus 1. When n minus 1 is set equal to m, n becomes n plus 1, a sub n becomes a sub n plus 1, and we're raising x to the nth power. So why are we doing this? Why are we reindexing these infinite sums? Well, notice x, y double prime, and y prime now, they have the same power of x to m. So we can combine these sums and just factor out x to m. And then notice we're going to do the same thing with y. It's going to be on the next page. Do the same thing with y. 2 times y is 2 times a n x to n. Here we replace m with n. I'm sorry, we replace n with m. And now we add these all together. So now all these sums are some coefficient times x to m. We factor x to m out. We get m times n plus 1 times a sub n plus 1. That was from x times y double prime. And plus m1 plus a times, m1, m plus 1 times a sub n plus 1. That was from y prime. Minus 2 am, that was from minus 2y. And so we have this sum, these two terms have a factor of am plus 1. This just has a factor of am. So we can factor out am plus 1 from each of these terms. And we get m plus 1 in parentheses squared. Or equivalently, if we distributed the m here, we get m squared plus m plus m plus 1, which is m squared plus m plus 1, or m squared plus 2m plus 1. So we get m plus 1 in parentheses squared times a sub n plus 1 minus 2am times x to the m is equal to 0. That's only possible. So as with polynomials, the power series actually work very similar. The way the power series work is very similar to the way the polynomials work. The only way they're identically 0 is if each term is 0. So we obtain the following equation. n plus 1 squared times a n plus 1 minus 2am is 0. That means a sub n plus 1 is 2 over n plus 1 and parentheses squared times am. If y of 0 is 1 and y prime of 0 is 2, that means that a sub 0 is 1, so a1 is y prime of 0, which is just 2. a2 is 2 over 1 plus 1 squared times 2. That becomes 2 over 4 times 2, which is equal to 4 over 4, which is equal to 1, or 1 over 2 times 2, which is 1. a3 is 2 over 1 plus 2 squared, which is same as 2 over 9. So that should have actually been like 2 over 9. So we can conclude that y of x is 1 plus 2x plus 1 half plus 2 over 9 times x cubed, etc. This means y of x is equal to the infinite sum am times x to the m, where am satisfies the recursive relation am plus 1 times 2 over m plus 1 squared times am. M is larger than or equal to 0, and we're starting with the term a sub 0 is equal to 1. Now notice y of 0 equal to 1, or a sub 0 equal to 1, started off this sequence, and we were able to determine a1 from a0, and then a2 from a1, and so on. However, so this is important, it is true, we could have just specified y of 0 was equal to 1 and gotten a solution. So what this means is that the series solution will work if y of 0 is 1. The series solution is uniquely specified by y of 0 equal to 1. Y prime of 0 equal to 2 is a consequence of the fact that we use a series solution. If we just said y of 0 equal to 1, we should know from the theory of second order ODEs that there should not just be one solution. There should be two solutions. Now, in this case, the problem really with this is that actually x equal to 0 ends up being a singular point for this ODE. Now, we never really have time to talk about that, but that's because if you divide everything through by x squared, then you have coefficients that are not defined when x is equal to 0. So that's really the problem here, and that's why if you have this series solution at x equal to 0, specifying the initial condition x equal to 0 means there's only one series solution with y of 0 equal to 0. I'm sorry, with y of 0 equal to 1. Now, it's possible there could also be another solution that could not be obtained with the series method where y of 0 is 1 and y prime of 0 is some other number. But in this case, y of 0 is 1, specifies y prime of 0 is 2, and we get the following series solution to the ODE. Now, I'm going to make sure that on your final exam, the extra credit problem will consist of specifying y of 0 and y prime of 0, where y prime of 0 or a1 will indeed satisfy the required recursive relation. Now, what's important here is not so much that detail of y of 0 and y prime of 2, but more this recursive relation. In fact, if you get to this recursive relation, you'll get at least 10 points extra credit. This y of 0 is equal to 1 and getting a sub 0 is 1, and a2, a1, a2, etc., that's going to be worth the other 5 points. Okay, so best wishes in the final. And just remember that the final is going to be uploaded this Monday by 12 p.m. You will have until Wednesday, May 13th, to complete the final and upload it in the Dropbox section of Lego.